This presentation introduces a unique simulation of isotope evolution in a molten salt reactor. As the reactor operates, all sorts of byproducts are created. In the graphic here, each element is a different color. Some elements are valuable, some are corrosive or otherwise troublesome. The proportions of each change over time, making for a very interesting and dynamic chemical soup. The molten salt reactor is aptly called the chemist's reactor. The overall goal of the project is to determine what's in the salt of an MSR at any point in its lifetime. The approach is to develop a simulation. The first major task is mostly done. I found most of the data I'll need on the internet. This now resides in a database. That part of the project is the subject of a separate presentation. The focus here is on the algorithms that drive the simulation. There are two new concepts to consider and later validate. First is the enormous span of time to be covered. Using exponential time steps for that is definitely something to be validated. Second, there are plenty of references to the decay formula for radioactive isotopes. However, they all assume the lump of decaying stuff is just sitting on a lab table. Let's assume the lump is 134 iodine, decaying to stable 134 xenon, which floats away. The lump only gets smaller. This is not the case inside a reactor where new iodine is constantly being created. A formula for that is not to be found on the internet, and my solution needs to be validated. So far, we are only considering the fission products. Fission products absorb neutrons, but so do fuel nuclei, and that's more important. This project won't be complete until we add the evolution of the fuel. One challenge for the model is the huge time span, from the first second to the billionth. Even a supercomputer can't model each individual second. We need to aggregate. Usually a model aggregates at the same scale. A map aggregates terrain features to a certain scale that is consistent across the map, except perhaps for insets. This model will have insets within insets, some 30 levels deep. That's fairly unusual, to say the least, and needs to be evaluated. The simulated reactor is very tiny. There's only one fission per second. We will calculate the fission products at the end of the first second of reactor operations rather carefully. That's because we will reuse that data a billion times. Exponentially, that's 30 doublings. A billion seconds is a bit over 16 years. Oak Ridge did design a reactor called the denatured molten salt reactor. The salt in that was supposed to last 20 years without cleaning. The exponential representation of time here would allow the user to create such a snapshot by adding two snapshots together. Notice the ampersand because this is a special kind of concatenation. We can't just slap the two files together. We need to decay the old isotopes before adding the new. The first second of reactor operations is important in this simulation. Nominally, one fuel atom is split, producing some 800 isotopes as immediate fission products. How does one nucleus split into 800? It doesn't. If it bothers you, think of a zillion fissions instead. The math works out the same. Tellurium-134 is the most popular immediate product, which I'm calling a native fission product. It's the purple block in the tallest stack. Over 6% of the time a fuel atom splits, it produces a 134 Te nucleus. 134 tellurium decays to 134 iodine in the blue block just above the purple. That decays to 134 xenon, which is stable. There isn't enough native 134 xenon to show here. It would be an orange cap on the tallest stack. There's lots more orange to the right, heavier isotopes of xenon. However, both 134 tellurium and 134 iodine have half-lives less than an hour. So after a day, if you stop making more natives, the whole stack will be orange. That's the isotope evolution we are trying to simulate. At the bottom of the 134 stack are the really unstable natives. Here are three: 134 indium, tin, and antimony. The tin and indium are too rare to rate even a pixel on the main chart, so this is a logarithmic scale. The antimony is pale green on both charts, and the bottom of the tellurium block is just above the green. Assuming an average decay time of half a second, beta-minus decay shifts some of the nuclei up the stack. The indium, with a half-life of a split second, is pretty much gone to form tin. The dark orange tin natives have a half-life of 1 second, so about 30% of the tin migrates up to the pale green block. Very little of the antimony decays, since it has a half-life of a whole 10 seconds. The upward migration would make a very nice animation of isotope evolution, but that's a bridge too far. We will have two methods of calculating radioactive decay in this model. Concurrent decay is used for the newest isotopes. Pure decay is used for the old isotopes. Concurrent decay is calculated only once. It takes the initial yields out to the end of the first second, when the first snapshot is taken. Here, the hottest isotope has decayed to a sliver of itself. The yellow isotope, initially the most popular member of this stack, loses about 20%, which migrates up to the cooler green. Concurrent decay assumes a steady state in the reactor. The nominal reaction rate is 1 fission per second, but here we will spread that out. The yellow proportion of 0.5 will be divided by 5, and will spread them evenly across the time step. Here we'll have 5 mini fissions at 0.1 seconds, 0.3, 0.5, 0.7, and 0.9 seconds. Those born early decay the most. The youngest, at the bottom, contributes most to the survivors in the yellow stack in the 1 second snapshot. In the next second, the old nuclei born in the first second will do nothing but decay. During that time, the second fission event occurs. Since it looks just like the first, in terms of initial fission yield and concurrent decay, we simply reuse that data. Then we put them together and divide by 2 to get the 2-second snapshot. Every new snapshot is created by doubling the current inventory of isotopes and subjecting the first half to pure decay. 29 more doublings produces the final snapshot, representing 17 years of operation. It's labeled 16 because 16 is a nice power of 2. The user can run the reactor almost twice as long by adding together all of the snapshots that made this last snapshot possible. That would be a gigasecond minus 1 of operations. At the moment, the user's first choice is made with a multi-select list. The display includes the name of the snapshot, which is also the length of the snapshot in seconds. The length in years is also shown, and the length in whatever units are most appropriate. At the bottom is the end of the simulation run. Here it is the sum of the two highlighted rows, 17 years and 6 months. The user also has the option of choosing the fuel ratio. At the moment this is fixed for the duration of the simulation run. Phase 3 of this project will allow the fuel to be varied according to a schedule. The data also allow different neutron energy levels, so we use that to represent different reactor designs. The user must enter a set of energy values according to the reactor design. This example is for a well-moderated reactor. This is for a fast reactor, which might be preferred if the goal is to eat used fuel rods. One of the most common arguments among MSR designers is whether slow or fast reactors are better. This simulation will only show that one is better for one customer and another is better for a different customer. The numbers the engineer uses come from a separate analysis of the reactor geometry, moderator, and choice of salt, among other things. Of course, the usefulness of such a simple treatment of a complex engineering challenge needs to be validated. The energy distribution will not change for the duration of the simulation, but it is possible that the salt composition could change by design. That would require Phase 4 for this project. The fuel mix and energy distribution are saved into separate tables, and the user will give each a name. The results for each simulation run will go into a database table that is indexed by the names of the fuel and energy mixes. Here the energy distribution is named JAG11A. The choice of salt is considered part of the reactor design. JAG11B could be the same reactor and moderator, but the salt proportions are different. If there are 800 different isotopes, there will be 800 times 30 records in this database. Here we see the once popular 134 tellurium represents a much smaller proportion of the fission products by year 8 than in the first second. By year 16, that is diluted in half as even more 134 xenon is created. Isolating on 3 isotopes from the decay chain for isotopes of atomic weight 90, there are 3 possible histories for any isotope. On the left is a short-lived isotope that reaches equilibrium. On the right is a stable isotope that simply keeps accumulating in a linear manner. It's easy to project the accumulation of these. We hardly need a simulation for most of them. It's the intermediate half-lives that cause the uncertainty. Strontium has a half-life of 30 years, so its history is still curving when the reactor is stopped. This affects its daughter products as well. The curve for stable 90 zirconium is not quite straight. Tracing the history of a particular isotope or element might be one of the uses for these data. The engineer will want to know at what point the palladium builds up past its saturation point. At that point it begins to plate out on the inside of the pipes, which is a good thing to know. The engineer might also be interested in the buildup of several neutron poisons as well. Further analysis is possible on the results of Phase 1, but they will be incomplete until we consider neutron absorption. The fission product proportions will change slightly as some of them absorb neutrons. But fuel nuclei can absorb neutrons as well, which is of greater importance. A fuel nucleus can become non-fuel, and a non-fuel nucleus can become fuel. Current nuclear waste can become fuel, which is one of the MSR's big selling points. With a validated treatment of fuel evolution, we might answer the question of how much waste an MSR can consume. The amount of heat energy that needs to be dispersed after a shutdown depends on the isotopic composition of the salt. These data need to be added to the database. Changing the fuel mix on the fly has already been mentioned. Until the model has a way of removing the fission products, it isn't much different from a solid fuel reactor simulation. A system that traps gases bubbling out of the salt is common to every MSR design. This and other cleaning schemes will reduce the population of certain elements at certain times. This is where we hand the reactor over to the chemists. Engineers would like to see more than a back-of-the-envelope estimate of the consequences of their design decisions. This simulation is intended to provide that. The user can control 3 dials, one for the fuel mix, one for reactor design, and the third governs the length of the simulation run. Whether such a simple scheme has engineering merit remains to be seen. This simulation really won't be useful until we cover neutron absorption properly. We also need to consider moving stuff out of the salt by various means. First, however, the use of an exponential timing scheme and the concept of concurrent isotope creation and decay need to be validated.